Hey guys, Mr. Backerberg here. In this video, we're going to look at definite integrals and area. If you've got a non-negative function, so if the graph of your function is above the x-axis and it's integrable over a closed interval from a to b, then the area underneath the curve from a to b is the integral of that function f from that a value to that b value. So an important part here is that your function has to be positive on that interval. So if you're looking between a specific a value and a specific b value, your function needs to be above the x-axis in order for the area underneath the curve to be the integral. Now, a little bit later on, we'll talk about what happens if your function is negative, but as long as your function is positive, then the integral is the area underneath the curve. So in this example, we are going to evaluate the integral of the function square root of 4 minus x squared dx from -2 to +2. Now, if we were to graph that out, we would see that our function actually gives us the top half of a circle with a radius of 2. So if we're talking about the area of a circle, well, we know that area of a circle is pi r squared. But since we have just half of a circle, then the area of a semicircle is going to be 1/2 times pi r squared. Now, since the circle has a radius of 2, we can fill that in for our r value. So this is going to be 1/2 times pi times 2 squared. Well, we know that 2 squared is 4, but half of 4 is 2. So this is going to simplify down to 2 pi. Now, because our function is positive on this interval, our graph is above the x-axis as we're looking between -2 and +2, then this integral value is that area of the semicircle that we just found. So the answer here, when we do the integration, is just 2 pi. Now, if we've got an integrable function that is non-positive, or if it's negative below the x-axis, then the Riemann sums for the function over that interval from a to b are the negatives of the rectangular areas. So then we can say that the integral of our function from a to b is the negative of the area for that region between the graph of our function f and the x-axis. So mathematically speaking, if we're dealing with a function that is negative below the x-axis, then as we do the integral, the answer is the negative of the area if our function is negative, below 0. Or we could also work this the other way around. We could say that the area is the opposite or the negative of the integral when our function is negative. So for example, if we were taking a look at this function where we've got y equals the cosine of x, if we wanted to find the area between pi over 2 and 3 pi over 2, well, talking about the area, it's the integral. So we are integrating the function cosine of x dx, and we're going between pi over 2 and 3 pi over 2. But because this is below the x-axis, because this function is negative, then as we're calculating this area, it's the negative of the integral. Now, we don't have the necessary tools in our tool belt to actually evaluate this right now. We'll get to that eventually. But for now, it's important for us to remember that since our graph is going below the x-axis, then that creates a negative area. Now, if we're dealing with an integrable function that has both positive and negative values over an interval, then the Riemann sums for the function add the areas of the rectangle that lie above the x-axis to the negatives of the areas of the rectangles that lie below the x-axis. So you're not getting a total area. What you're getting is some cancellations. So some of that stuff below the x-axis is going to cancel out some of the area that's above the x-axis. So the value of the integral is the area above the x-axis minus the area below the x-axis. So as we're calculating this integral, so we're integrating this function f of x from a to b, we find the area above the x-axis and we subtract off the area below the x-axis. So in this example, we're going to look at finding some integrals by giving you a little bit of information. So it's a fact that the integral of the sine of x from 0 to pi is 2. So as we're looking at this picture in here, from 0, so 0 is right here, pi is right here. So this area between this curve and our x-axis, that has an area of 2. So we're going to use that information and a little bit of intuition to help us find a few more integral values. So the first one that we're going to look at is the integral from pi to 2 pi of the sine of x dx. So from pi to 2 pi is this right-hand side of our graph. Now notice that looks very similar to the left-hand side, but it's below the x-axis. So because it's the same size except below the x-axis, then this should give us an answer of -2. And it's a negative area because it's below the x-axis. Now again, same set of information. We know that the area between 0 and pi for this sine of x function is 2. But now we're going to look at the integral from 0 to 2 pi for the sine of x dx. So now we're going from 0 all the way over to 2 pi. Well, we know that this top area is 2. In the previous example, we said that this area below the x-axis was -2. So if this part is 2 and this part is -2, then the total integral from 0 all the way to 2 pi is just going to be 0, because that -2 is going to cancel out with that +2. Same set of information again. So we know that this area from 0 to pi, that has an area of 2. But now we're going to look at the integral from 0 to pi over 2 of sine of x dx. So pi over 2 is going to be right in the middle here. Now if we know that this total area is 2, but instead of going all the way over to pi, we're going to stop at pi over 2. So we're just going halfway in here. So then this integral value should just be 1. Now, same information that we were given before. We know that the integral from 0 to pi for sine of x dx is 2, but now I've changed the function a little bit. It's not just sine of x, now it's 2 plus sine of x dx. Well, here's what we know. That 2 plus in there really just takes our sine function and shifts it up 2 spaces. So if I just draw in a line straight across from 0 over to pi, then this area up here is still 2. But now we've got this extra chunk below our graph that we need to account for. But that ends up just creating a rectangle. Now the width in here of this rectangle, well, we're going from an x value of 0 over to an x value of pi. So this width in here is just pi. As far as the height, we're hitting this y value of 2. So then as far as the area inside of this rectangle, if I take 2 times pi, then that's going to give me an area of 2 pi. Now, as far as this integral from 0 to pi of this 2 plus the sine of x, I'm going to take that 2 that we already knew from that curved portion, and I'm just going to add on that 2 pi that we just figured out from that rectangle. So then the total integral, or the total area underneath this curve, is that 2 plus 2 pi. Now, same set of information. Integral from 0 to pi of sine of x dx is 2, but now we're looking at the integral from 0 to pi of 2 sine of x dx. So what that 2 does in front is it makes your wave go up to an amplitude of 2. Normally, if we were just looking at this regular sine of x, then it would just have a wave height of 1. So since we've got a wave height that's twice as big, well, we knew that this integral up here was 2, but if we double the height of the wave, it might make sense to us that the integral would be double the size. So this integral is going to have a value of 4. Now looking at this example, same exact information. The integral from 0 to pi of sine of x dx is 2, but now we're changing things just a little bit. So now we're doing the integral from 2 to pi plus 2 of sine of x minus 2 dx. Now that x minus 2 inside of the parentheses, that minus 2 in there takes our graph and shifts it to the right 2 spaces off of that x value of 0. And so what we're looking at on this integral is we're looking at that x value of 2, and we're going over to pi plus 2. Well, pi plus 2 is this value right here. So if we're looking at the area underneath that curve between those x values, it's going to be the exact same thing as this original integral value that we were given. All we've done is shifted everything over to the right 2 spaces. We shifted the function to the right 2 spaces, but we also shifted our integral to the right 2 spaces. So we get the exact same answer of 2. Same exact information for this one. So the integral from 0 to pi of sine of x dx is 2. Now here we're looking at the integral from negative pi to positive pi of sine of u du. Now notice that we changed the variable in here, but that really doesn't matter. The letter that we're using for the variable does not matter. The process is still exactly the same. Now we're doing negative pi to positive pi. Well, we know from 0 to pi, that area is 2. Now on the left-hand side, we're going from 0 to negative pi, and that chunk of our graph is below the x-axis, but it's the exact same size. So this is going to have an area of negative 2. This has got an area of positive 2. So if we go from negative pi all the way over to positive pi, then this is going to have an integral of 0. That's going to be it for this video. Thanks for watching.